Today I'm going to be talking about infections transmitted via the respiratory route, and this is part of a series of lectures on the different routes by which major infections get into the body. And the reason this is important is that the route of transmission is key both to understanding how the disease is transmitted, but very importantly also how we can combat it. And combating things by one route is very different from diseases transmitted by a different route. I've talked already in this series about vector-borne diseases passed on by insects or arachnids, the oral route, food and water in particular, about sexual and blood-borne transmission, important diseases, for example, like HIV. And today I'm going to be talking about one of the major routes of transmission, the respiratory route. Now, I'm thinking about routes of transmission. Usually most infections have either a single route of transmission or they have two routes, but one of them is dominant. I'm going to be talking today about diseases where the principal route of transmission is respiratory. Now, if you're from the infections point of view, from an evolutionary point of view, the respiratory route has got several advantages for the infection. Unlike some routes, such as oral or vector, it does require, for transmission, the person who's infecting to be near the infected person, but not necessarily at the same time. So, for example, someone can produce droplets or aerosols, and then someone can come into a room later, so that they don't have to be in exactly the same time. They don't need to know the person that they're transmitting. This, for example, is very different to the sexual route, where people almost invariably know the person they're transmitting to, and they do not need to touch them. So therefore, to have a stranger in a crowded room, but with an infection, someone can actually spread that infection around several households, because in a sense, from an infection point of view, each household is separate, and then people can go home and then they will infect their own household because infections within households are very efficient. So it's a very useful way of spreading disease around between strangers who happen to be in the same place at roughly the same time. But to work, the infection has got to be viable outside the host for long enough to get from the infecting person to the infected person, and many infections cannot do that. Now, several major infections have evolved to take advantage of the respiratory route of transmission. And I'll be talking about several of them, not all of the ones I'm listed here, in the second part of this lecture. They include the mycobacteria, things like tuberculosis, bacteria, including pneumococcus, which is a major cause of pneumonia, meningococcus, a major cause of meningitis, but also major diseases of historical importance like plague, which is passed on partially by vector and partially by respiratory routes, atypical bacteria, things like Legionella, and many viruses, including measles, flu, COVID-19, and smallpox, the only disease so far to have been eradicated. Some fungi can also be transmitted via the respiratory route, but I won't be covering them. They're a relatively small group, mainly in immunosuppressed people, but very important in that group. Now, the respiratory route of transmission usually has several different routes by which it can be achieved. Probably the most prominent, certainly the one that people have concentrated on historically, are droplets. Droplets that people produce when coughing, sneezing, laughing, shouting, or even just breathing. The second is objects that these droplets could have landed on that people can then touch and then touch their own faces, which we all do unconsciously the whole time. And some of these droplets and the infections from them can be quite persistent on surfaces for a number of hours or even longer. The third route is aerosols. And aerosols are different because they can hang around in the environment for a lot longer, and they can spread through the environment in a way, as we'll come back to, droplets are less likely to. And the way you combat those is therefore rather different. And then not strictly airborne or respiratory in the ordinary sense, but mouth-to-mouth contact, particularly kissing, would be an example of this. Now, because droplets are important, just a little bit about the ballistics of droplets. A droplet is an object which once coughed out or sneezed out or produced in ordinary speech will then travel a certain distance, and then it drops to the floor with ordinary gravity. So it's like ballistics, it's just like ballistics, for example, in artillery. And the cough or sneeze can extend the range and increase the number of droplets, but they're still subject to gravity. They're still going to go downwards. And they may contaminate surfaces for some time. Very small droplets, however, can remain suspended in the air for a long period of time, and these are the ones which can tend to lead to wide areas potentially being contaminated. But usually with droplets, you have to be relatively near someone and relatively near the period of time that they produce them. Although the route of transmission of the diseases I'll talk about is the respiratory route, infections transmitted via that route can cause damage throughout the body. Some infections transmitted via the respiratory route cause their main damage in the lungs, including pneumonia, and that's the route which in a sense is the most obvious. But many others cause most of their damage elsewhere in the body. So although it's come in through the respiratory route, it's other bits of the body which tend to cause the major problems for the person infected. Several of the major causes of meningitis, for example, are passed on by the respiratory route. Sepsis and generalized inflammation is often transmitted this route, diseases that cause this. Diseases of the nerves, for example, leprosy is passed on by the respiratory route, and diseases of the heart, diseases like diphtheria. So these are diseases which can be dangerous for any part of the body, even if they actually came in through the respiratory route in the first place. Medical staff, doctors, nurses, and others divide respiratory infections into upper respiratory infections, things that cause most of the trouble from infecting the upper part of the airways, the mouth, nose, throat, very upper airways, and lower respiratory tract infections, which tend to affect the lungs. Many of the trivial infections that we think about that are passed on by the respiratory route, things like coughs and colds, are upper respiratory tract infections, but the upper respiratory tract is also the route by which many very serious infections get into the body. They don't go as far as the lungs, they just infect the upper part of the airways, or at least that can be the principal route by which they get in. Lower respiratory tract infections are things like pneumonia in particular. And some infections can be both. And actually an example of that is COVID-19, which has both an upper and a lower respiratory presentation. Now, the body is not defenseless to these droplets and aerosols that come into the airways. We have multiple layers of defense. The first and probably the least aesthetically pleasing, but actually incredibly important to all of us, is mucus, otherwise known as snot. Very important, it's a physical barrier, and it's constantly being excreted. It traps viruses and bacteria. It can, via enzymes, damage them. Antibodies are as part of it. And there's what's called the mucociliary escalator, which gets mucus all the way from the lungs up, and then people cough them out or swallow them. So this is a very important way in which many infections are stopped really at the first point of contact. Behind this, though, are several layers of immunological defense, and the body's ability to respond to infections, something we've discussed at several points, is really quite remarkable. First to infections that the body has not seen before, first time round, and then also a learned response, which actually is when they see the same infection a second time round. This, of course, is the basis of the fact that people have less severe disease often the second time, and in particular is the basis of vaccination, your own immune system's ability to learn. Now, stopping transmission via the respiratory route is more difficult than some of the other routes that we've considered before. So, for example, when we're talking about the oral route, the extraordinary engineering feats that have made it much less likely that things will be transmitted by that route. Much harder when all you have to do is have several people in a room at the same time. But there are several things we can do to reduce the risk of respiratory transmission. The first, arguably the easiest, is to be outdoors. What you get is rapid dilution of droplets and aerosols, generally much more spaced out people, much less crowded together. Ultraviolet light, several reasons mean that outdoors is much safer. Now, of course, if someone coughs inadvertently in your face from a couple of feet's distance, then you're actually at risk of catching an infection. But it is much safer in an outdoor environment. The second, something which, of course, we've talked about a lot during the COVID pandemic and will continue to, improving ventilation indoors. The natural ventilation, opening the windows, remains a very important way of doing this, obviously harder in winter months. And also, particularly in large buildings, engineering in ventilation whilst keeping in heat. Those two are often in tension, and the engineering challenge is to keep the heat in whilst keeping the ventilation going. And then finally, in terms of these physical environments, either keeping people at a distance, again, something we've all got used to during COVID, or direction, making sure when people are closer that they're seating side by side or back to back, or physical barriers. These are particularly useful, in fact, for droplet spray. They have less effect on aerosols. Just a quick digression into the very important issue of ventilation, something I think we really need to take very seriously as a result of having seen what has happened during COVID and indeed as happens in every winter with respiratory infections. Engineers, via the route of ventilation, yet again, improve public health. And I've talked a lot in this series about how engineering has underpinned a lot of the improvements we've seen in reductions in transmission. So here are some three sort of broad kind of examples, and there are many. On the left, we have really the simplest. This is a TB sanatorium, and the children that have been infected have been put just near very large open windows. This is just straightforward mountain breezes going through. In the middle, we have two examples, a schematic and then a local landmark of ventilation using heat. And here, engineers put ventilation at the bottom of the building, and then they have a chimney towards the top, and the heat rises, and it pulls fresh air in from the bottom up through the system. And what an example of this is the central tower of the Palace of Westminster, as I say, a major landmark, which is designed via heat to help ventilate the whole building. And then really at the more extreme end of the engineering challenges, we have buildings which actually have got sealed windows. On the right here is UCLH Hospital, where in fact I and many other colleagues work. And this requires mechanical ventilation because you can't use natural ventilation for a variety of reasons. So these kinds of ventilation are essential, and we need, I think, to take this much more seriously now that we've seen the impact of having insufficient ventilation in many public buildings. Personal behaviours can also reduce the chances of passing on or acquiring respiratory infections, and most of them are common sense that people would have handed down from their parents and grandparents. Staying at home and self-isolating when unwell with a seasonal respiratory infection. Struggling into work with a streaming cold is not actually remarkably helpful to your colleagues, often quite the reverse. Maximising social time outdoors or with good ventilation where that's possible. Covering mouth and nose when coughing and sneezing. This is an old campaign that's been running for many years, illustrated here from some decades ago. Washing hands and disposing of tissues is a way in particular of making sure that droplets that have got onto objects don't lead to infections by people touching something and then touching their own face. And in periods of high transmission, something which I think the importance of we've really begun to recognise during COVID, the use of face masks, which can reduce both the impact and distance of droplets and also aerosols, which can lead to other people being infected. So these are things people can themselves do to reduce the risk to others. And all of us have been doing them during the last 2 years. There are some broader things which also tend to drive respiratory infections. There is a very strong correlation between poverty and deprivation, relative and absolute deprivation, and many respiratory infections. Then the reasons for this, in a sense, are fairly obvious in most cases. Housing, being poor and very crowded very often. Working conditions, often again being cramped, poorly ventilated. Diet and malnutrition, making it much easier for people to be susceptible to infections. And then there's the wider access to vaccines and curative medical services. So when you look at maps of many of the respiratory infections, they correlate quite closely with maps of poverty around the world, and indeed within the UK. And if you remember all the maps we've seen of COVID, they've tended to get very heavily concentrated in areas of relative deprivation. As poverty has decreased, this is the positive side of this, many infections have as well, and I will go through a few of those in the second half of the talk. Smoking, when it comes to respiratory infections, is a self-inflicted wound. There is really clear evidence that of increases of many respiratory infections among smokers, includes tuberculosis, influenza, pneumococcal pneumonia, and many others. And the main reason for this probably is that it damages the lungs' defences. Additionally, people who've got very damaged lungs as a result of this, chronic obstructive airways disease, a really serious and unpleasant long-term disease group as a result of smoking, are very vulnerable to respiratory infections. But even people who smoke more likely than that are at greater risk of infection. And then there are some occupations which increase the risk of respiratory infections. Those include close contact occupations, so healthcare workers, for example, who have to come and properly have to come close to people, social care workers, but also workers, for example, taxi drivers and people who are also involved in public services, security guards, anyone who's front of house but has a lot of contact relatively close to multiple strangers are at potentially greater risks. Then there's a group of occupations that damage the lung defences. Mining, for example, whether it's coal mining or gold mining. Gold mining is a very big risk, for example, tuberculosis. Many other occupations that cause dust are likely to increase the risk of someone acquiring an infection. And then some occupations may increase the risk of specific infections and the response to them. For example, fungal diseases and zoonotic diseases from animals are unsurprisingly more common among people who are in farming or livestock. Important when considering how to address these, respiratory infections tend to be highly seasonal. Not all, but the great majority. They include, in particular, infections where the population immunity is in rough balance with the infection. And in winter, several changes occur which are to the advantage of the infection. They include more time together inside, windows shut, ventilation reduced. This is really because of this tension between keeping heat in and keeping ventilation going. Lower temperatures and changes in humidity. Outdoors, lower ultraviolet light. There are a variety of things, but in particular, crowding together indoors is a high risk. And here what I've illustrated is several different years of influenza in the UK, and the size of the wave is different depending on which year it was, but when the wave was very stereotypical. It's over the late autumn and winter months. And the same is true for many other of these infections. Now, medicine has developed against these, in addition to the control measures I've talked about, engineering and personal behaviours in particular, there are medical countermeasures. And for many of the major diseases, the medical countermeasures have been highly effective. Broadly, drugs, such as antituberculous drugs, TB, antibiotics against bacterial diseases and antivirals, so treatments, but also depending on diagnosis, so diagnostic tests are needed before you get to the drugs in many cases, and then vaccines. And we have effective vaccines for some, but not all, of the infections via the respiratory route. And where they exist, they have transformed the picture. Some prevent infection altogether, and others are effective at preventing severe disease, but don't prevent transmission so easily. So they vary in terms of how effective they can be. And I'd like to illustrate this with several major infections, starting off with the group of infections who have their impact across many parts of the body. And the first, and historically one of the most important, still important in many areas, tuberculosis, TB, still a leading cause of death worldwide. It was common absolutely everywhere, killing people in all walks of life, including in the UK. When we think about more recently, I'm just taking a pre-COVID thing, in 2020, around 10 million people who fell ill with TB and 1.5 million people died, included around 1 million children who were infected. So TB is still very much alive and around in the world, but it is much more heavily concentrated in countries where there is significant poverty. It's mainly spread by droplets via the respiratory route, and people can be chronically infected. What we have here is an X-ray of someone who's got chronic infection and infectious, spitting out or coughing out TB over many years. People who are malnourished and people who are immunosuppressed, for example, those with uncontrolled HIV, are most at risk now. When the NHS started here in the UK, TB was a very major cause of mortality. And what we have on the left here is a graph, the top line showing, and this is a logarithmic scale, the top line showing there's been a steady reduction in the number of cases, and in the bottom line, an even steeper reduction in the number of people who've died of TB. And the same is shown in a slightly different way on the right. The green boxes are people who died of infection, and TB was very heavily involved in this. And what this shows in different age groups over different decades from 1915 onwards. And in the first few decades of the last century, infection really dominated the causes of mortality across very large numbers of the age groups. And then steadily that has improved. And this is a combination of medical countermeasures, drugs in particular, in the case of TB, and improved living standards. In a pre-drug era, and also pre-HIV, without treatment, smear-positive TB, these are people who got a lot of TB, they're coughing a lot of bacteria around the system, had a mortality of around 70%. And this would happen over about 10 years, so over really quite a long period. People who got less TB, a rather lower mortality, and they were less infectious, but those were broadly the two groups. And the treatment for these had to be really often quite dramatic, because people otherwise would have died of their disease and sometimes still did. Examples were collapsing lungs, and what I've illustrated here is something called plombage, where material was put into the lung to try and collapse it down and kill the TB by scarring. This is really all that was available until the first effective drug in 1946, a drug called streptomycin. And we now have highly effective treatments for the great majority of TB. And the key to preventing the spread of pulmonary TB, TB of the lung, is early diagnosis and then 6 months of directly observed multi-drug therapy. On the left are the drugs people would typically take, usually a smaller number after the first couple of months. And on the right, one of the buses that goes around London, finding people who are homeless and checking they don't have TB because they're at particularly high risk, and then treating them if they do. So it's very important to go out to find people and then to treat them, because this is both a preventable disease, a serious disease, and a highly transmissible disease. Now, TB is a respiratory transmitted disease. It does cause problems in the lung, but it is not just a lung disease. And so although old-fashioned consumption with lung disease killed many in the pre-treatment era, you've got TB meningitis, a very dangerous form of meningitis, generalized TB, so-called miliary TB of the whole body, TB around the heart, TB of the spine, and what we've got here is an MRI of the spine with someone who's got TB, of the kidneys, of the glands, and of the lymph nodes. So TB can get all around the body. It's not just in the lungs. And this is typical for some of the major respiratory infections that we have to deal with. There is a vaccine for TB. This is BCG, and this does help prevent severe disease, but it has a limited impact on transmission. It remains one of the most widely used vaccines in the world, but it's fairly effective at preventing severe TB in children, less effective in adults, less effective in low-income settings for a variety of reasons, and less effective against lung TB. And there are a variety of new vaccines, but so far none of them have really proved a significant improvement on this really quite old vaccine. So for TB, rather like for HIV, which we talked about in the last lecture, really the main basis of prevention is finding cases and treating early. The outlook overall has some very major pluses over the next decades, but also one significant threat. As internationally development is occurring, people are moving out of poverty. The general reduction in global poverty, improvements in living standards, improvements in curative care are likely to lead to reductions in TB over time. We're getting improved diagnosis, and there are improving treatments, including shorter courses of treatment. And HIV has driven a lot of TB, and the very effective treatment and, in some areas, prevention of HIV is also going to help have an impact in improving TB. The threat, however, is that we do have significant multi-drug resistant TB, remembering that the basis of prevention of TB is treatment. And this map shows where this is concentrated, and it's actually concentrated in particular in some areas, including, for example, Eastern Europe. The other major mycobacterium of humans that's transmitted this way is leprosy. And I'm illustrating this not because it's a common disease now, it is much less common than it was, but because here's an example of a disease that you would not think of as a respiratory infection. But this is, in fact, how it's thought to be transmitted. One of the most feared and stigmatized diseases, if you look through both historically and now. And transmission is probably through droplets from the nose and mouth. Transmission needs very close, prolonged contact. This is not something you would catch from being a few meters away from someone in a room. Its effect, however, once it's got into the body, is really devastating for individuals. Destroys nerves, can make people blind, and has a whole variety of impacts as a result of that. And this gentleman here, you can see the effects of leprosy on him, and you can just see what that would do to his life chances. There is, however, effective multi-drug treatment, some similarities to TB treatment, and BCG, the same vaccine, is actually a fairly effective vaccine against leprosy as well. And so this disease, which had tens of millions of cases as late as the 1960s, is much rarer now. Many people are still living with the after effects of leprosy, but in terms of new cases, this is now fairly highly concentrated in a small number of countries. I'd now like to illustrate a few other examples of diseases which go through the respiratory route but have their effect elsewhere in the body. And diphtheria is another very major example of this. It used to be a major cause of death, particularly in children. There were over 1 million cases before the 1980s. It's mainly transmitted by droplets. And it then colonizes the throat, and the photo here really shows a typical example of someone with the diphtheria infection of the throat. But the damage is caused by toxins, which are released by the bacteria, and they can either cause massive swelling in the throat, which can compress it, almost strangling the person who has it, or they can circulate in the body and causes what's called heart blocks. So the heart can be highly affected and in some cases essentially stop working, or peripheral nerve damage. So this is sitting in the throat but causing its life-threatening effects very often a long way from that. Diphtheria has almost entirely gone from high-income countries now. And this is a combination of improved living conditions, people being less crowded, antibiotics to treat people when they have disease, and vaccination, which is around 95% effective. And if you look at the time over a long period, you can see the downward pressure of diphtheria, largely by improvements in living. But on the right, what you can see is what happened to diphtheria when vaccines came in. So they had an extraordinary impact in reducing this major killer of children. Another major killer of children, also now very rare, rheumatic fever. This came from streptococcal sore throat, a slightly different picture on the back of the throat you can see here. Again, spread by droplets. This is not the infection causing the problem, but the immune response to the infection can cause really serious damage to the body. And three things tended to happen: joint swellings, this is why it's called rheumatic fever, problems with the brain, people had significant neurological problems, and also the skin. But the really major one was problems of the heart, and this caused lifelong damage in children to heart valves that would cause them problems for the rest of their life and increase their risks, for example, of stroke at an early age. So rheumatic fever caused by streptococcal sore throat, another example of a generalized disease from the throat. With us still, but again, significantly improved as a result of modern medical countermeasures, bacterial meningitis and septicemia. And the classic case for this is meningococcus. It's carried by about 10% of adults in the nasal throat, just completely normally. And it's transmitted by close contact, coughing, kissing, but not by quite casual contacts, but people have to be relatively close. It can cause really rapid onset meningitis or septicemia, as seen in this child, and her parents decided they really wanted people to understand how serious this disease was so that they could prevent it, or both. And a child can be playing in the playground in the morning and intensive care by the evening. It's extraordinarily rapid onset. Untreated, a very high mortality, around 50%. It's antibiotic sensitive, so you can treat it, but you have to get in early. And there are a variety of different types of it. Which one's important depends where in the world you are. But fortunately now, we have effective vaccines available for all of them. Globally, the most important ones are meningococcus A, which is really dominant in Africa, and B and C, which are dominant here in the UK, although rarer. There used to be massive epidemics of meningococcus A in West Africa, particularly in the Sahel region. These have been virtually eliminated by vaccination, and there's been over 70% decline in meningitis cases. In the UK, we've had a significant reduction in invasive meningococcal disease, as I say, potentially fatal disease in children, from over 2,500 cases at the turn of the century through to about 755 more recently. And we've had first meningococcus C vaccine available since 2000 and meningus B MenB vaccine since 2015. As a result of these, we've seen a steady reduction in these major causes of meningitis in children and also, in fact, in adults. The other major bacterial cause of meningitis in children was Haemophilus influenza B, HIB, despite its name, a bacteria rather than a virus. It was the commonest cause of meningitis in the youngest children, those under 4, again passed on by droplets, coughing and sneezing. 1 in 20 children who got this died. 1 in 5 who survived were left with serious neurological disability that would be lifelong. The HIB vaccine was introduced in UK and Ireland in 1992, and it reduced the incidence by more than 90%. And you can see, again, the dramatic impact of the vaccine when it was introduced on this major cause of meningitis, death and disability in children, and then a catch-up campaign when there was a bit of a resurgence. So really big impact from this vaccination. Measles is a disease which I think is underestimated by many people. It's spread by coughs and sneezes, again. It's incredibly infectious. So if you're in a room with immune-naive children or indeed adults, and people around the person who's infected, around 90% of people would catch it. So this is extraordinarily easy to catch. And it can be in the air for up to 2 hours after someone has actually left the room. So it's not even necessarily you're actually in the room with them. When it occurs in epidemics, particularly in areas of poor nutrition, the mortality rate can be extremely high. And a mortality rate of 5 to 10% can be seen in big epidemics, particularly in areas where there's low vitamin A. Vitamin A is a very major protection against measles. Fortunately, there is a highly effective vaccine giving largely lifelong protection. The great majority of children are vaccinated against it through MMR, and that has led to a significant reduction in this disease. But it's not just the mortality that is associated with big epidemics we need to be aware of. It's also the fact that it can cause significant rates of measles encephalitis, inflammation of the brain, which can either be fatal or leave people with lifelong brain damage. So about 1 to 3 in 1,000 children with measles will develop encephalitis with measles. Of these, around 10 to 15% will die, and a further 25% will be left with permanent neurological damage. This is not a trivial disease. In addition, about 1 in 1,000 children with measles will develop post-infectious encephalitis. This happens later on, and about 1 in 25,000 will develop a much later thing called subacute sclerosing panencephalitis, again, inflammation of the brain, up to a year later, usually fatal. So this is very serious indeed, potentially. And this is in comparison to much lower rates of people who would develop any problems with the measles vaccination. So the benefit to risk ratio is really way over towards vaccination. And I've illustrated this with the very sad example of Olivia Dahl, Roald Dahl's daughter, to whom the Big Friendly Giant and James and the Giant Peach were both dedicated. She got measles, got encephalitis, and died. And Roald Dahl campaigned for parents to get their children vaccinated as a result of that. The other two infections which are in the MMR vaccine, which are also transmitted by the respiratory route, are mumps and rubella, both almost entirely vaccine preventable. In pre-vaccine days, around 1 in 4 cases of viral meningitis in children were from mumps. And mumps is passed on by direct saliva and droplets. Rubella is otherwise known as German measles, a significant risk slightly later in life. This is a risk in particular in women who are pregnant, a significant risk for miscarriage, stillbirth, and fetal abnormalities, particularly if women catch it in early pregnancy, again passed on by droplets. All 3 of these diseases, measles, mumps, and rubella, are prevented by a single vaccination. So those are diseases which are diseases of the general body, but where the transmission is via the respiratory route, and very often the infection doesn't get any further than the throat. Then we move on to pneumonia. Now, pneumonia, which is inflammation and often significant gas exchange problems in the lung, can be caused by bacteria, by viruses, and occasionally by fungi in the immunosuppressed. I won't deal with that in this talk, but in people who've got significant immunosuppression, this is a serious risk. Very common. Around 450 million cases a year globally of pneumonia. And in the pre-antibiotic era, these would have killed people throughout their lives, so including young adults were susceptible to dying of pneumonia. As a result of treatment, deaths now tend to occur in the very young, the very old, those living in less wealthy countries, and people who are immunosuppressed. So those are the groups who tend to die, but pneumonia can happen at other stages. In many parts of the world, pneumonia is the commonest cause of mortality, particularly in children and particularly in low-income countries. But even in high-income countries, pneumonia is a significant cause of mortality, particularly in older adults. And if you go into any hospital ward, particularly in winter, you'll see many people who have pneumonia, many of them very sick. The most common bacterial cause is pneumococcal pneumonia. And this is a bacteria which is carried in the throats of many adults and over half of preschool children, so it's really common. It's transmitted by droplets and by secretions, and it causes a pneumonia, which is the commonest cause of pneumonia, certainly in the UK and probably globally. It can be treated with antibiotics, but obviously you need to do so relatively early on. And this is an X-ray of someone who's got a lobar pneumonia, which would typically be pneumococcal pneumonia. But it doesn't just cause pneumonia, it also can cause meningitis and a generalized sepsis. And this is particularly a risk for young children under 2 and people over 65, as illustrated in this painting. There's a very high mortality from pneumococcal meningitis, and roughly 1 in 5 survivors will have significant disability, again, for the rest of their lives. There is a fairly effective vaccine against pneumococcus, but it's not as effective as the MMR vaccines, for example, but it is certainly well worth having for something which is extremely common. And it's given slightly differently in children and in older adults, who are the 2 groups who are most at risk. And you can see in this graph what happened when the initial vaccine against 7 of the different types, because there are several different types of pneumococcus, were introduced in the UK, first in 1996. And there was a real substantial reduction in pneumococcus as a result of this particularly invasive disease where it's picked up in the blood. But a slight increase in other forms of pneumococcus, and then that was replaced by something which covered 13 different types of pneumococcus, and there was a further reduction. So this is a good vaccine. It's had a very big effect when it comes to people who have got serious illness also in older adults. And again, what you can see is the initial vaccine reduction. The types that were affected by that vaccine went down, the other types didn't, and then we brought in the second one with 13-valent vaccine and further reduction in pneumococcus. So these vaccines have a significant effect on invasive disease. They do also reduce pneumonia, and what this shows, these are data from the USA, and they do lead to a significant reduction in the number of hospitalizations from pneumonia, but a lot of people still get pneumonia. So this is a good vaccine, but it is only partially effective, not fully effective. Now, it is still much better to have a vaccine which significantly reduces your risk of the most severe forms of infection and has a reduction in chance of pneumonia, but we shouldn't see it as something that eliminates it completely in the way that some of the other vaccines can do. And looking at pneumonia globally, under 5 deaths due to lower respiratory tract infections, pneumonias, have decreased by an estimated 37% just in the decade 2005 to 2015. And I would expect that to have continued when this study is repeated. I would expect this improvement to have continued. This is a combination of vaccines being available, antibiotics being available, and improved living conditions coming together to lead to a significant improvement in child mortality from pneumonia. Alongside these bacteria, and there are several others, I've just concentrated on pneumococcus in particular, viruses make up a very large proportion of pneumonia, so a lot of viral pneumonias. And of course, those pneumonias do not get better when you give people antibiotics. They are a large portion of pneumonias, but a much smaller proportion of deaths. The bacterial pneumonias tend to be more severe, although you can get significant pneumonias with viruses as well, particularly in children, something called RSV, respiratory syncytial virus, and influenza, both in children and in older adults. Currently, no vaccine for RSV, and as we'll come on to, influenza tends to vary by season and year. Now, influenza, which is the most important of these that we really had for the general population until very recently, has a very seasonal pattern. And so for seasonal flu, endemic flu, it comes in with some predictability in the great majority of winters. And what you see is the annual rate of flu globally since 2009-10, when the H1N1 swine flu pandemic occurred globally, and then what's happened every year since. And some years globally have been more cases than others, but every year there's been a flu outbreak in the winter. The exception is the last year, and so far in the UK this year, where rates of flu have been incredibly low. And the reason for that is that people have been doing things like social distancing, which have reduced significantly the risks of a whole range of respiratory infections. And we've seen a real reduction in many respiratory infections as a result, particularly flu. And therefore, as a positive benefit of this, over these 2 years when hospitals have been full of people with COVID, flu rates have been much lower. But we can anticipate they will re-establish themselves as measures are released and people go back to more normal behaviours over winter. Now, although you tend to see flu occurring every winter, how big the peak is varies substantially year on year in the UK and indeed in every other country. And sometimes a year will be a lot worse, and sometimes a year will be a lot better. They will occur at the same time, but the size of the peak can be very substantially different. And on the left, what I've got is influenza-like GP consultations showing the difference between the 2009 pandemic year, huge numbers of consultations of GPs, and a typical flu year, where the numbers are much lower, and then the last years where almost none have been seen at all. At the same time, some of these flu viruses are more likely to cause severe disease than others. And that is a combination of the intrinsic property of the virus, but also how well matched the vaccine is to the flu, because flu changes every year. Every year we develop vaccines that are meant for the seasonal flus, but if one of them is slightly less well targeted, you can have a more severe flu year. So it's a combination of the virus and the vaccine. And what we have on the right here is the annual cycle of increasing mortality in the winter and decreasing in the summer. That happens in all of Europe. And on top of that, the black lines, the blue lines is kind of the underlying rate. On top of that, the black line is the excess mortality. And what you can see is some years, substantial excess mortality above what you'd expect. In other years, is pretty well bang on what you'd expect. And that's because in certain years, the flu either was more severe, was more common, or was less well matched to the vaccine. By contrast, the H1N1 influenza pandemic of 1918, just over a century ago, probably killed, estimates vary quite a lot, but 50 to 100 million people globally. And people died of primary viral pneumonia and also of a secondary bacterial pneumonia. And it killed, and that may well have killed even the majority of people, and that would be much less in this era because of antibiotics. But this was a really massive impact globally. And two things are probably worth highlighting. On the right here, just for a sense of perspective, the number of people in the US who died in the 1918 flu pandemic compared to the total number of people who died in every war the USA took part in, World War I, World War II, Korea, and Vietnam. And if you put all of those together, more people died in this single pandemic. So it was a really massive event. It happened incredibly fast over a relatively short period of time. And importantly, it had a very different pattern of severity and who died to what we've seen with, for example, COVID, and what we see in a typical flu year. So in a typical flu year, what you see is very elderly people and very young children are most at risk of flu. In the flu pandemic, those groups were at risk, but also on the left, what we have is the ages, a significant peak of people who are young adults. And as a result of that, there was mortality all across the age spectrum. This is quite different from, let's say, COVID, where apart from people who are immunosuppressed, the really big heavy burden of disease in terms of mortality and severe disease has fallen almost entirely on older citizens. Which brings us finally to COVID-19. Now, I've done a full lecture on COVID early in the pandemic, and I'm not going to cover the same ground, but many of the things I laid out there remain current. Some of them have moved on. And I've also talked about the vaccines in a lecture about vaccines. So I don't want to, again, cover things I've recently covered on this. But I think there are some important things to bring out from COVID-19, which is a major respiratory transmitted pandemic. The early transmission, I think everyone knows, started in Wuhan and then spread rapidly through China and then rapidly worldwide. So this demonstrates the extraordinary speed at which a respiratory transmitted infection, because it can transmit between strangers, can actually achieve, and its global spread was over a matter of weeks. Prior to COVID, we had experience of 4 previous human coronaviruses and 2 other coronaviruses that had jumped species into humans. The 4 human coronaviruses, named rather snappily 229E and similar names, generally cause colds and sore throats. They're often quite common, and they're very rarely serious. At the other extreme, we'd had 2 coronaviruses. The first of importance, not chronologically, but is MERS-CoV. This has been passed on mainly by dromedaries in the Arabian Peninsula to humans, and some human-to-human spread. This has typically had a 35% case fatality rate. And there was one significant outbreak in South Korea in 2015, brought under control by public health measures. We also had, slightly earlier, SARS, which came from coronaviruses in bats in China, almost certainly. Just over 8,400 cases, less than 1,000 deaths, but this did have a significant mortality rate, so somewhere between 11 and 15% case fatality rate. So for the coronaviruses, we had experience of both mild forms and more severe ones. COVID-19 fell between these two. The thing which I want to really highlight in this talk, in addition to points I've made in previous ones on COVID, is just really to look at what has happened in the UK, as an example, over the period that we've been suffering this pandemic, remembering that it is only 2 years since the first cases arose in the UK. The first wave that we received in the UK, we had very limited diagnostic tests. In fact, one of the issues we had is we didn't really see the wave until it had actually started putting people into hospitals because there weren't sufficient diagnostic tests. We had no known treatment for it. We had no vaccine, and we didn't know whether we were ever going to get a vaccine at that stage, and we had no population immunity at all. We were therefore entirely dependent on social measures to limit damage from cases, hospitalizations, which threatened to overwhelm the NHS, and deaths. And it was due to everybody taking really extreme social distancing measures, because those were the only things we had to limit spread through the population, that we brought this wave under control and prevented the NHS being overwhelmed and many more deaths than would otherwise have occurred. There was then a beginning of a wave that was from the original variant, and then the alpha wave on top of that, which occurred in the winter of last year. By that stage, we had good diagnostic tests, so we saw this at a fairly early stage, and it allowed us to help concentrate our care much better. There was better hospital treatment. Several things had been developed that led to mortality rates going down. We had some early vaccine rollout, but only to the very top end of the age range when this really was going, and no antivirals at that stage. So we were still heavily dependent on social measures, although we could see an exit by this point because we had a vaccine and we were beginning to get better treatments. By the point that the Delta wave hit, which was really the third major event, we now had vaccines rolled out, so we had really quite high levels of protective population immunity, not complete, but really quite high. We also had better treatments on top of the ones we previously had, still have the diagnostics. So we did need social measures, but they were more limited because we were able to put a lot more weight on the medical countermeasures of vaccines, drugs, and diagnostics. But we still required population measures. And finally, we had the Omicron wave, which we are still in the throes of. And now we have a vaccine plus a booster. We have some antivirals, so some people are being detected early and treated, and that stops them developing severe disease and going to hospital. And we also had a less severe variant, but still substantial numbers of hospitalizations. People say this is mild. This is not mild. It is still more significant than seasonal flu. It's still substantially more significant than other coronaviruses, but it certainly is a less severe variant, and that's an important part of what has happened. But in countries where there's less vaccination, the impact of the Omicron wave has been significantly greater. So if we just look at what happened on these, and these are familiar charts, but I want to make a general point about this. This is COVID cases over time, and what we see is the first wave really we didn't see because we didn't have the diagnostic capacity. This is really a case ascertainment problem. But by the time we came to the second wave, initially original variant and then the alpha wave, significant, what we thought was a very large wave at that stage, brought under control in both those cases by people doing very significant social distancing and taking all the measures that were so difficult for the population. And as a result of that, although there were a large number of deaths in these waves and a large number of people did end up in hospital, the impact was much less than it would have been if those social distancing measures had not been in place. In the Delta wave, we were able to get away with fewer social measures, still using them, but fewer social measures, and it happened particularly in summer, which probably helped to some degree, and it was extended there for over a longer period. Significant numbers of cases, but over a longer period. And then the Omicron wave hit, and what you saw was an absolutely massive spike. And this is the size of spike we could easily have got with previous variants if people had not done the social distancing. So this is a clear demonstration of what would potentially have happened if people had not acted as they did. How did this translate into hospitalization? Well, as you'd expect, the first wave led to substantial numbers of hospitalizations, brought under control by social distancing. Second wave also led to substantial numbers of people in hospital. The NHS was, a very large proportion of the NHS was taken over to treating COVID, and as a result, people couldn't treat cancers and heart disease and many other things. Only by bringing COVID under control was it possible to bring the NHS back to doing what it needs in all those other diseases. And then the Delta wave, a prolonged period of people in hospital, but a lower rate because of vaccination. And then there has been a significant increase in hospitalizations with Omicron. And again, you don't end up with 17,000 people in hospital in the UK in winter unless people have got significant problems. So this was a non-trivial wave, but look at what's happened to mortality. And this is not the mortality rates that are usually quoted in the various briefings, which are about COVID-specific ones. Sadly, we've had a very large number of people who died entirely due to COVID or partially due to COVID. In terms of it's on the death certificate, so over 176,000 people have died due to COVID. But this is all-cause mortality, so this includes people who died for other reasons as well, including pressures on the health service. And you can see very big increase in excess mortality in the first wave, very big increase in excess mortality in the second wave, brought under control by people's actions. But then you see an excess mortality over a prolonged period, but nowhere near that size with the Delta wave, and that's because of the effect of vaccines and, to some extent, better treatment. And with Omicron, really much less impact. That's a combination of widespread vaccines, boosters, better treatment, and a less severe variant. So a real change in terms of the mortality pattern we're seeing as a result of medical countermeasures, and you can rely much more on them and less on social measures. So in summary, Infections transmitted via the respiratory route is an extremely effective route of transmission, and what has happened with COVID, I think, demonstrates just how effective the respiratory route can be. It can affect, but once in the body, infections can affect all parts of the body, and I gave examples of infections where they get in by the respiratory route, but the damage is done in many other parts of the body. Medical countermeasures, drugs, vaccines, diagnostics, have substantially reduced the impact of many of these infections via this route. Simple social measures, ones that people should be perfectly happy with, like staying at home if you've got a very bad flu, and ventilation, which is something we should all be aiming for, particularly in public buildings, can reduce transmission. But they will remain a major cause of hospitalisation and mortality for the lifetimes of everybody watching this. Medical countermeasures have really changed this, but nevertheless, many of these remain very potent and long-lasting threats. Thank you very much.